Not too long ago, when we talk about Newton's laws, let's say I have a block like this one, or a car parked on an inclined plane, and it's not moving. It means it's in a static equilibrium. The forces, the obvious forces acting on the object are the mg, this one here, the normal force, and the friction force. How did we solve questions similar to this one? The first condition is the sum of the forces equal ma, but if a is 0 because the system is at equilibrium, the sum of the forces are going to equal 0. So we going to make this one equal 0, and we break the equation into components. In this case, very easy. I'm pretty sure everybody by now should be able to do this. The x and y axes are set up according to this system coordinate here. The fs is positive mg sine theta, and you guys know how to break mg into components, right? This is mg cosine theta. This is your theta right here, and this one right here is mg sine theta, and you take it from there, right? And you go fs minus mg sine theta equals 0, fn minus mg cosine theta equals 0, and you solve for whatever they're asking for. So that was easy, right? How about if the objects are different from this one, objects that have tendency to rotate? A typical example, a plank with the length L and a mass 5 kilograms is hanging by means of two strings at two different points, not symmetric with respect to the center of mass. If you want to solve for T1 and T2 in cases like this, the first step is always using Newton's second law. Sum of the forces acting on a given object in static equilibrium equals 0. There are two tensions, T1 and T2, acting straight up, and mg is acting straight down. To solve for T1 and T2 using just this equation is impossible. Two unknowns, one equation. So what do we need to do? We need another equation, and we are going to get it from the torques. In other words, the sum of the forces equals 0, the sum of the torques also equals 0. How do we handle torques? We need to always decide about an axis of rotation. An axis of rotation is always chosen in such a way to make the solution easy. There are three obvious points here where you can choose the axis of rotation. You can choose a point right where the center of mass is, you can choose a point where T2 is acting, or a point where T1 is acting. So those are three possible points. But I'm going to tell you right now, and you're going to notice later on why. The best point that you're going to select is that one that is going to eliminate one of the unknown quantities. T1 and T2 are unknown, so choose your axis either at point T2 or T1, but I'm going to choose it at T1 because evaluating the lever arms from this point is easier. So this is going to be the axis of rotation for this particular system. Alright, the sum of the torques is going to equal to 0. There are three torques. For each force there is a torque. There is a torque due to T1. There is a torque due to T2. There is a torque due to mg. Three forces, three torques. They all add up to 0 because the system doesn't spin. Okay. Now we need to break this one into components. Notice that the axis of rotation is right here. So that point is supposed to be fixed. It doesn't move, doesn't turn. How about mg when it acts? Notice if mg is acting down this way, it means that it's trying to spin or to rotate the plank in the following direction, the clockwise direction. However, the T2 is trying to pull up, trying to turn the system about this axis in the following direction, which is the counterclockwise. This is exactly what the interpretation of the component going to be when it comes down to torques. You choose counterclockwise as positive or negative. It really doesn't matter for cases where the sum of the torques equals 0, static equilibrium. And in my case, you're going to find me for the most part choosing the counterclockwise to be the positive and the clockwise to be the negative. Therefore, T1, since it's acting right where the axis of rotation is, the lever arm is going to be 0, therefore the torque is going to be 0 also. T2 is trying to turn counterclockwise, positive. The torque of T2 equal T2 times the lever arm. Where is the lever arm for T2? It's all the way from this point to the axis. This is it. What's this quantity? L over 2 plus L over 4. That is 3L over 4. So this is the lever arm for T2 if the axis is chosen to be where T1 is acting. Now, mg, which way is mg acting? It's trying to turn the system clockwise, negative torque, according to our system coordinate, equals mg times the lever arm. The lever arm for mg is just from the center of mass all the way to the axis of rotation, which is L over 2 only, equals 0. Notice here that the L is going to cancel. Solving for T2, you're going to obtain 2 mg divided by 3. And this is T2. Now, how can I solve for T1? All you need to do is you go back to the equation that we obtained from the sum of the forces, plug in the T2 right here, and solve for the T1. And the answer is going to be T1 equals mg over 3.